Hello and welcome back. In this video we'll be discussing the SN2 reaction mechanism. So this is the more important substitution mechanism that we'll be discussing in this chapter. We'll also look at the SN1 mechanism. So the SN2 mechanism is a concerted mechanism where everything happens all in one step, but the stepwise mechanism, or the SN1 mechanism, has two steps. So we're going to look at our two main steps. So we're going to look at those independently. So the concerted mechanism, this is the SN2 mechanism, involves breaking of the bond to the leaving group and making a bond to the nucleophile at the same time. So what are our players in this reaction? So we've got an alkyl halide, or something bearing a good leaving group. It doesn't have to be an alkyl halide. And so that is called our electrophile, or our E+. We can abbreviate it as E+. And then we have a nucleophile. In this case, the nucleophile is written over the arrow, but it can be written as just plus NU and then having an arrow, okay? The nucleophile is going to have a lone pair or a high region of electron density. It doesn't have to have a negative charge, but for the SN2 reaction, we normally see a nucleophile with a negative charge. Okay, so here we have a nucleophile, and we have two reaction arrows. So the nucleophile with its lone pair and negative charge, which is normal for the SN2 reaction, is going to attack at the alpha carbon. That's the carbon bearing the leaving group, okay? And it's going to kick that leaving group out. So it attacks at the alpha carbon and kicks out the leaving group. And then it forms our product, and the leaving group leaves. So these are our players. We've got an electrophile that is usually an alkyl halide. It can be just an alkyl, an sp3 hybridized carbon with some leaving group. We've got a nucleophile. It's going to replace the halogen or the leaving group, and we've got a product plus a leaving group after the reaction takes place. Okay, so the SN2 mechanism is that concerted mechanism where we have the nucleophile attacking, leaving group leaving, all in one step. We'll look at the rate equation for that reaction and the diagram for that in just a little bit. Okay, but we can also have a stepwise mechanism, or an SN1 mechanism, where we have the leaving group leaving first, and then the nucleophile attacking at the carbon that was the alpha carbon. Okay, so the leaving group leaves from the alpha carbon, then the nucleophile attacks at that carbon that was bearing the leaving group usually. And then we have the product plus the leaving group. Now, sometimes you can get rearrangements and the nucleophile may be attacking at a different carbon, but we're just going to keep it simple for now, okay? So this stepwise mechanism is going to be covered in a later section. So for our concerted mechanism, again, nucleophile attacks at that alpha carbon, leaving group leaves. So those are our steps. These two steps happen all at one time, so it's a concerted mechanism. They're all actually happening in one step. So we have nucleophilic attack, loss of leaving group in one step. That is a concerted mechanism. Okay. All right, and so then we have our product plus our leaving group. Okay, so this is the SN2 mechanism, which stands for substitution nucleophilic bimolecular. Okay, so what would be the rate law for this reaction? The rate is equal to some K times the concentration of the substrate times the concentration of the nucleophile. Why is that? Because there's only one step in this reaction. If we look at the reaction diagram, we've got energy versus progress of reaction here. We've got our starting materials at some energy, and our products at probably a lower energy level, and we're just going through one step, and we'll look at this again in a minute, but we're just going through one step to get from starting materials to products. So that step is our rate determining step because we only have one step. So what does that mean? It means that we have to have the substrate and the nucleophile both involved in that rate determining step. So if you double the concentration of the substrate, you're going to double the rate. If you double the concentration of the nucleophile, you're going to double the rate, because both of those species are required for that rate determining step to happen. They're both involved in that rate determining step, which is just the only step in this reaction. So we get an inversion of stereochemistry in this reaction. So what happens is, here's an example reaction here, okay, where we've got, let's first identify our players, okay. We've got our electrophile here that's got the alpha carbon bearing the leaving group, okay. Then we've got our nucleophile that's going to do the attacking. Then we form our product plus the leaving group that has left. Okay, those are our players in this reaction. So what's happening in this reaction? The nucleophile attacks from the backside of the carbon bearing the leaving group. It attacks from the backside of the leaving group and kicks the leaving group out. Okay, so that happens all in one step. That's called backside attack. Okay, and when that happens, what we get is now the nucleophile that was the nucleophile is now attached to the backside of that alpha carbon. Okay, so what does this end up doing? It flips this molecule like an umbrella. It flips it like an umbrella that's flipped up in the wind. So we had the configuration where the hydrogen and methyl group are pointing to the left. Now we have the configuration where the hydrogen and methyl group are pointing toward the right. So the nucleophile becomes attached to the other side of that carbon. So what's happened is we've swapped the configuration, and this is called inversion of configuration. So we get inversion of configuration at the alpha carbon. The alpha carbon's configuration is inverted. What does that mean? That means if we had an S configuration, then chances are when in the end we're going to have an R configuration. So it always flips, but the only time we don't go from, say, S to R or R to S would be if that nucleophile was lower priority than one of the other groups that's attached. So this might not be 100% true, but we always get inversion of configuration. You don't always go from S to R or R to S, but more than likely, if you had an S configuration, at the end, the product is going to be the R configuration, okay? So if you had an S configuration in the starting material, your product will be R configuration. If you had an R configuration in the starting material, your product will be the S configuration, unless there's some anomaly there, such as you had another higher priority group already attached to that alpha carbon, okay? But you always get backside attack for an SN2 reaction, and you always get inversion of configuration for the stereochemistry. All right, so practice drawing products with Skill Builder 7.1. I forgot to pop that in here, so we'll have some problem. Yeah, I got some problems down here, okay? All right, so I'm not really going to cover this molecular orbital theory here because I don't really consider it to be relevant to our discussion. So I'm going to go ahead and skip that. All right, so what do you think the transition state is going to look like? Remember we talked about that energy diagram, okay, where we had energy versus progress of reaction. We had our starting materials forming products here, and we're going through one hump to get from starting materials to products. Well, we're overcoming that activation energy, that one activation energy in that energy diagram to go from starting materials to products. That's our activation energy, okay? And what do we have at the top here? At the top, we have a transition state. What is a transition state? It's where bonds are forming and bonds are breaking. It's where we're going from starting material to product. It's where that action is taking place. To draw a transition state, we put everything in brackets just like we do with resonant structures, but we also have this double dagger symbol up here on the right indicating that that's a transition state. So if we wanted to draw the transition state for this reaction, notice this reaction here. We've got our nucleophile on the left, which is SH minus. The nucleophile is going to be usually negatively charged. It may be a neutral species with a lot of electron density. Then we have our electrophile here, or that's also called a substrate. Okay, and that's going to have a partial positive on the carbon bearing the leaving group. The nucleophile attacks that alpha carbon, kicking out the leaving group in the SN2 reaction all in one step. So when that happens, right in the middle, and that reaction is occurring, right when that nucleophile is coming in, we're going to form a bond from the nucleophile to the alpha carbon. And then we're going to break the bond between that alpha carbon and the leaving group. So in the transition state, those bonds are forming and breaking. So in a transition state, we've got bonds forming and bonds breaking. Okay, so in this transition state, our transition state is our carbon. The transition state for our carbon is planar. Okay, that's going to be all in the same plane. We've got that configuration flipping. Okay, it's right in the middle of that flip. Now we've got a bond forming to our nucleophile. That's going to be our new substituent. And we've got a bond breaking to our leaving group. That's leaving. Okay, now this looks like too many bonds to carbon, but these are partial bonds, so it's not really a too many bonds to carbon situation. We've got partial bonds, partial charges. Okay, so we've got partial negative here, partial negative here, partial positive in the middle. We've got bonds forming, bonds breaking. So that's what the transition state looks like as we're going from starting material to products. This bond on the left is forming. This bond on the right is breaking. Okay. Now notice that we had the R configuration on the left, and we have now the S configuration on the right after our nucleophile adds. So we flipped configuration. We get inversion of configuration going from starting material to products. All right, so here now we're going to practice. Draw the transition state for each of the following SN2 reactions. So why don't we, in addition to drawing the transition state for these reactions, why don't we also draw the reaction itself? Now we already have the product here, but let's just go ahead and look at what's happening so that we fully understand. In this reaction A, we've got hydroxide as our nucleophile. Why is that the nucleophile? Okay, that's the nucleophile because sodium has a positive charge. It's over on the left side of the periodic table. It's not going to be doing anything here. It's just a counter ion. Hydroxide has lone pairs and a negative charge. That's going to be our nucleophile. Okay, our electrophile is this alkyl halide on the left. Okay, the carbon bearing the bromine is where the reaction is going to take place. The hydroxide is going to attack that carbon and kick out the leaving group, giving us the product plus the sodium bromide over here. The bromide is our leaving group. Okay. Now, what would be the transition state here? The transition state is right when this hydroxide is attacking that alpha carbon and the bromine is leaving. So we draw the carbon and then we draw what's attached to it in a planar configuration. So I've got a hydrogen. These two hydrogens here are not shown, right? So one of those hydrogens is going to be coming out at me. The other one's going back. And then I've got the molecule. The rest of the molecule I'm going to draw at the bottom, okay? And then, of course, this is all going into brackets with the double dagger up here on the right. And I've got a bond forming to the hydroxide and a bond breaking to the bromine. Remember, we've got partial bonds and partial charges. So I've got a partial positive on the carbon, partial negative on the bromine. Because remember, that bromine leaves with the two electrons from the bond. It's going to leave with the lone pair and negative charge. The hydroxide had a lone pair and negative charge, so it's partial negative here. It's bringing that lone pair in to form a bond to that carbon. Okay, so we've got a bond forming on the left, breaking on the right. Okay. For this next reaction, this nucleophile is called acetate. It's the counter ion to acetic acid when it's the conjugate base for acetic acid. Okay, so that acetate anion can act as a nucleophile, attacking the alpha carbon on the iodine, kicking out the iodine, giving us this product. So here's our alpha carbon, and now we have the nucleophile, what was the nucleophile, now attached as a substituent. So what did our transition state look like? This carbon had 2 hydrogens, so very similar. We've got a carbon with a hydrogen coming out, hydrogen going back, and then the rest of the molecule, which was 1, 2 carbons. So we could just draw a line and say ethyl for those 2 carbons. Now, this is a transition state, so we've got brackets and a double dagger. We've got a bond forming to the acetate and a bond breaking to the leaving group, which is iodine. So we've got partial charges, partial positive on the carbon, partial negative on the iodine, because that iodine is leaving, taking its 2 electrons in the bond with it as a lone pair. We've got a partial negative over here on the acetate. It's coming in with its lone pair and negative charge. I don't have a lot of room here, so I think I'll just do the last one. Okay, so for C though, we had hydroxide as our nucleophile. This alkyl chloride is our electrophile. So the hydroxide is going to attack, kicking out the chlorine, leaving us with the what was this electrophile now has an OH attached. Okay, so we've substituted the chlorine for the hydroxide. Now for this, so I'll let you guys draw the transition state for that one. I just don't have enough room. So for the next one, we've got SH minus is our nucleophile. Okay, because remember sodium is Na plus, so this is going to be SH minus, just like OH minus. Our electrophile is this species, this cyclohexyl bromide, okay, or 1-bromocyclohexane, okay, and so the alpha carbon is here in blue. The SH minus is going to attack, kicking out the bromine and replacing it with the SH, and then we have the bromide as our leaving group. So this is our electrophile, nucleophile, product, and leaving group. Okay, so now what does our transition state look like? This one's a little bit tougher because we have, let's see, at that carbon bearing the bromine, we've got hydrogen, and then we've got the other 2 carbons. Okay, and we've got to orient this such that the bromine is leaving. So we've got carbon with the bromine leaving. So this is going to be a little more challenging to draw. Okay, so then we've got a hydrogen. Let's do the hydrogen coming out. Okay, and then we've got the cyclohexane ring, which is like this. Okay, something like that. And then we've got the nucleophile coming in with a bond forming to the nucleophile. That's the SH minus. So we've got partial negative on that, partial negative on the bromine, partial positive on the carbon bearing the leaving group. Okay, so this should actually be a dash. Okay, so this reaction is governed by some strong kinetic factors, where we see that the most reactive type of alkyl halide to this reaction is a methyl halide. The second most reactive is a primary, okay, meaning it has 1 alkyl group, meaning it has 2 hydrogens on that alpha carbon. Okay, next we have a secondary, so that's going to be the second the third most reactive, or the second least reactive. Okay, so that alpha carbon has 2 carbons attached. Okay, and this is a general trend. And then tertiary, where the alpha carbon has 3 other carbons attached, is essentially unreactive toward an SN2 substitution mechanism. Now, we'll see that we can get some reaction with the SN1 mechanism for tertiary alkyl halides, but for SN2, for this reaction mechanism, it's unreactive. The most reactive is methyl, second is primary, secondary is kind of iffy, we'll get a small reaction there, and then tertiary is unreactive. Why is this? Is because we have more steric hindrance. So why don't we go back up and look at this reaction again. So let's say that we have sodium hydrosulfide plus chloroethane. And what's that going to give us? This SH minus. Let me erase this, and I'm going to erase the sodium here for clarity. But just remember that sodium is there as a counter ion, okay? Oh shoot, I don't look for anything. Okay, so SH minus attacks at the alpha carbon, kicking out the chlorine. Okay, so then our product is this, and I'm not drawing stereochemistry here because neither of these is, the alpha carbon is not chiral, so it doesn't matter. Plus, and then our product is NaCl, okay? All right, so that's the overall reaction. So think about this. We've got these two hydrogens here at the alpha position. Hydrogens don't take up a lot of space. So this SH minus can get in there and reach the alpha carbon, kicking out the chlorine. So for a primary alkyl halide, there's plenty of room. But if we had, say, a tertiary alkyl halide, and this thing's trying to get in here and reach this alpha carbon, these methyl groups are large. Okay, they're going to take up a lot of space. So, if you think about that, if we drew like a space-filling model of this molecule, these methyl groups are blocking the entire backside from backside attack, and that's what we have to have. So when our nucleophile tries to attack, it can't get in. There's no way. It can't reach that alpha carbon. So that's why the tertiary alkyl halide is less reactive. In fact, it's essentially unreactive toward an SN2 reaction. So if we look at this reaction here, where we've got an alkyl bromide reacting with iodide in acetone, in this case, as a solvent at 25 degrees C, we get the alkyl iodide plus the bromide. Okay, so these are different alkyl groups. These are examples of the reaction rate for different alkyl groups. Okay, so the fastest one is going to be methyl bromide here. You can see if we give the bromoethane a relative rate of 1, then the methyl bromide is 145 times faster than the ethyl bromide. So this is a primary. Ethyl bromide is a primary alkyl halide. Now on the next one we have a secondary alkyl halide because the alpha carbon has 2 carbons attached. So this is isopropyl bromide, and so that one is going to have a rate that's 0.008 or 1,000 times relatively slower than the ethyl bromide. So it's way slower than the primary. Then for the tertiary, the T-butyl bromide, it is negligible. There's not going to be really any reaction for the tertiary. Okay, no reaction because the nucleophile can't get in here. It's trying to hit the back side. It can't get in. For secondary, there's still a lot of steric hindrance. But for the ethyl, we've only got these 2 hydrogens here. They don't take up a lot of space. We can get a good reaction. Okay. Now, those are at the alpha substituents at the alpha carbon. But if we move on to the beta carbon, if we move away from the alpha carbon, we can see there's an effect on those substituents as well, from those substituents as well, okay? So if we give that ethyl bromide again a relative rate of 1, okay, then the 1-bromopropane is going to be 0.8, so a little slower. And then if we have the 2 carbons attached, then we're going to have 0.04, so it's about 10 times slower. And then if we had, this is called neopentyl bromide, this is going to be way, way slower. Way, way slower. Essentially no reaction because even though this is a primary alkyl halide, this neopentyl group takes up a huge amount of space. So sterics are a factor in this reaction. whether that nucleophile can get in there and do the reaction. Okay, so sterics are huge in this reaction. All right, so when we're talking about rate, we're talking about the activation energy for this reaction. How much energy does it take to overcome this hump and get to products? So we're going from starting materials here to products, and for thermodynamics, we're talking about our delta G or our delta H here of the reaction, okay? So how stable are the products versus the reactants? But the main thing we're concerned with right now is being able to overcome that activation energy to get the reaction to go, okay? So here we have the cyanide reacting with methyl bromide to give us this product here where we have the cyano substituted and bromine. So our transition state here is the cyano group coming in, the bromine leaving, okay? And so we've got partial bonds and partial charges. This is for methyl bromide. So remember, that's going to be the fastest reaction. Our nucleophile attacks from the back side, kicking out the leaving group, and our transition state happens right here at the top of that energy diagram, right at the top of the peak of that activation energy. That's where we're going to see that transition state. So if we consider the energy diagrams for a methyl substrate versus primary versus secondary, remember tertiary isn't going to happen at all. For tertiary, the energy diagram is so high, or I'm sorry, the activation energy is so high that nothing's going to be able to overcome it, right? Then our activation energy is lower for methyl versus primary versus secondary. So secondary is higher than primary, which is higher than methyl. Why? When the nucleophile is attacking here at this alpha carbon, for a methyl substrate, it can reach that alpha carbon easier. With the primary substrate, we've got that partially blocked. So that was, remember, about 1,000 times slower. And no, I'm sorry, the primary was what? The methyl is 145 times faster than the primary. And then the secondary is 1,000 times slower, right? Okay, so the nucleophile can get into the backside of a primary substrate, but with secondary, we have quite a bit of steric hindrance here from these methyl groups. Okay, so it's much harder for a secondary substrate, and so we have a larger activation energy. And tertiary is just too slow to measure. So if we had something like neopentyl bromide, like we talked about earlier, okay, even though this is really a primary alpha carbon, we've still got these big methyl groups here that are taking up space, and so they're going to hinder the reaction rate, and essentially we don't get a reaction with that one. So we talked about sterics. We talked about the stereochemistry of the SN2 reaction. We talked about sterics affecting the reaction rate. Another thing that affects the reaction, whether the reaction can actually move forward, is something called nucleophilicity. In other words, how does our nucleophile affect the rate of the reaction, or how does the nucleophile affect the probability of this reaction occurring? Okay, we need to have a good nucleophile in order to perform an SN2 reaction with that concerted mechanism. So we need a strong nucleophile. Okay, so a strong nucleophile is going to be something generally with a lone pair and a negative charge. Now we're going to see that we can also have a strong nucleophile that is neutral, but those are a little bit rarer. We're going to look at some of those in just a minute. Okay, so a strong nucleophile is generally something with a lone pair and a negative charge. So if you see something that's negatively charged, that's your nucleophile. Okay, so nucleophile attacks the alpha carbon, kicking out the leaving group. It's going to be much faster with a strong nucleophile. If you've got a weak nucleophile, something that's neutral but still has a lone pair and a negative charge, okay, something like water here in this case, then this reaction is essentially not going to happen for an SN2 because it's just not going to have the strength to do that backside attack and kick out that leaving group. That's going to be very slow, okay? So we need to be able to recognize a nucleophile as being strong or weak. So the strong nucleophiles are things like chlorine, bromine, iodine, okay, and the sulfides, okay, and hydroxides and cyanides, okay. Now, something that also can act as a good nucleophile for SN2 are some neutral sulfides or amines, but we don't have those on this chart. So, so if you have something with a sulfur, that's generally going to be a good nucleophile. Okay, the weak nucleophiles are basically water and alcohols. So the neutral water and neutral alcohols. Okay, so strong nucleophiles favor the SN2 reaction. Weak nucleophiles, as we're going to see, favor SN1. They favor a different mechanism. Okay, so for an SN2 reaction, you need a strong nucleophile. Now, sulfur is polarizable because it is lower on the periodic table than oxygen, and so it makes a good nucleophile sometimes even if it is neutral. So something like dimethyl sulfide can be a good nucleophile even though it's neutral because it has a larger atom, takes up more space, and it's what's called polarizable because the atom is larger than oxygen. It's kind of fluffy, the electron density is bigger, and so it can actually access that alpha carbon a little bit easier in order to perform this reaction. All right, and so we also need a polar aprotic solvent for an SN2 reaction. So here's some examples of those. So polar aprotic solvents are like acetone, DMF, the HMPA, acetonitrile, DMSO. Why are these polar aprotic? Because let's just look at acetone here. It does not have a hydrogen that can easily be pulled off, okay, or donated, and so it's not very acidic, right? And so it's also polar because the oxygen is withdrawing electron density from the carbon, leaving you a partial negative here, partial positive here. But these on the left are protic because they have hydrogens that are on heteroatoms like oxygen, nitrogen. Even if you had a hydrogen on a sulfur, that would be a protic solvent. Okay, so for an SN2 reaction, we need a polar aprotic solvent. So polar protic solvents engage in hydrogen bonding and stabilize the anionic species, okay, in order to decrease their reactivity. So aprotic solvents stabilize both the cations and the anions. Okay, but let's look at some examples of this. I don't know if we've got an example. Oh, here it is. Okay, so let's look at what this is. So if you had a let's say chloride ion, okay, and you put that in water, then the water is going to hydrogen bond or form an ion dipole bond with that chloride. Okay, because the water's got this partial positive here. Okay, and that partial positive is very good at stabilizing the negative charge. Okay, so water can also, let's say that we had sodium chloride as our nucleophilic species, because we're going to dissolve sodium chloride. Chloride's going to be our nucleophile. Okay, so the positive charge is also stabilized by the water. The partial negative end of the water. the oxygen end, right? And all the way around that sodium, then we have these waters. And that's why sodium chloride dissolves in water. So we form a solvent shell around the sodium with the negative end of the water around the sodium, and we form a solvent shell around the chlorine with the positive end, partial positive of the water around the chlorine. But that solvent shell that's around that chloride is going to protect it from being reactive. So it's going to keep it from reacting with the alpha carbon, so with the electrophile, because it's solvated. It's surrounded by all of these partial positives. But a polar aprotic solvent, the partial positive is way down here inside, okay? And it can't really surround the nucleophile. Let's say we dissolve sodium chloride in here again, okay? So we've got this negative end up here because it's polar that can associate with the sodium. So that's our partial negative of our solvent molecule. So we can form a solvent shell around the sodium, but not around the chloride. So when this sodium chloride dissolves in the polar aprotic solvent, the sodium ion will dissolve and be solvated by that solvent shell, and when it does, it will pull the chloride up into solution with it. But that chloride doesn't get solvated by the solvent shell, and therefore the chlorine doesn't have to break free from the solvent shell in order to react as a nucleophile. Therefore, the chloride is free, and so that's called a naked nucleophile. Okay, it's called a naked nucleophile. And so a polar aprotic solvent is going to start out with the nucleophile. Remember, our starting materials are here on this chart. Our nucleophile is going to be at higher energy, so we're going to have a lower activation energy to overcome than if we were in a polar solvent that's going to start our starting materials out at lower energy. We're going to have a higher activation energy to overcome. So aprotic solvents, or solvents that don't have that hydrogen on a heteroatom, are going to be better for SN2 reactions. Okay? Now, we mentioned that we need a good leaving group for SN2 reactions. In fact, we need a good leaving group for any kind of substitution reaction. So remember, leaving groups are generally the conjugate bases of strong acids. Those are our best leaving groups. And for non-biological systems, that's generally what we see. But we can even have leaving groups in biological systems. So for methylation, okay, in a biological system, we can put a methane on with this really big, stable leaving group here. So this is a good leaving group that's used in biological systems. Okay, so that's just an example of how we can see SN2 reactions even in biochemistry. All right, in the next video, we'll move on to E2 reactions. Thanks for watching, and I'll see you next time.